Today, we're going to pull back the curtain on a secret recipe, one that connects pretty much everything, from the music in your headphones all the way to the strange rules of quantum physics. It's an idea that shows how almost every signal in our universe is built from the exact same simple ingredients. Let's get right into it.
I mean, really think about that for a second. How on earth can the sound of a full orchestra, all that richness, all that complexity, get squished down into a tiny digital file that fits on your phone? What's the secret sauce that keeps it from just sounding like, garbage?
Well, the answer isn't some brand new piece of technology. Nope. It's actually a wild idea from way back in the 19th century from a mathematician named Joseph Fourier. He made this incredible claim that anything that repeats, and I mean anything, the sound of a violin, the glimmer from a star, you name it, can be described as just a sum of simple, pure waves. So, Fourier's truly radical idea was that any repeating pattern, no matter how jagged or complicated it looks, could be built from a surprisingly simple set of ingredients. Let's see exactly how that works. This is the heart of it all, the Fourier series. It's a mathematical promise, really. It says you can take these simple, smooth sine and cosine waves, think of them like pure musical notes, and by adding them together in just the right amounts, you can perfectly build a copy of any repeating signal. Okay, so let's see this in action. Here, we're trying to build a really sharp, blocky square wave. Now, by adding just 10 of our simple sine waves, you can already see the basic shape starting to form. It's a little lumpy, sure, it's not perfect, but the foundation is totally there. All right, let's add more ingredients to the mix. Now with 50 waves thrown in, look at that. The approximation gets so much sharper. The sides are way steeper, the tops are flatter. The more simple waves we add, the more dead-on our reconstruction gets. And here's the kicker. This is not just some clever math trick. This is a fundamental truth about how our universe works. From the vibration of a guitar string to the orbit of a planet, any pattern that repeats can be built from these simple foundational waves. It's incredible. So, if every signal is just a mixture of simple waves, how do we find the exact recipe? How do we know how much of each wave to use? Well, that's where this idea of the spectrum comes in. The spectrum is, quite literally, the signal's recipe card. It tells you the exact frequency, you can think of that as the pitch, and the amplitude, or the volume, of every single sine wave you need to build it back up. Every signal has its own unique spectral fingerprint. A prism is the perfect way to think about this. It takes what looks like plain white light, and it reveals it's actually made of a whole rainbow of colors hidden inside. Well, Fourier analysis is a mathematical prism. It takes any complex signal and breaks it down into its fundamental frequencies. Okay, this all works perfectly for signals that repeat over and over again. But what about the rest of the universe? I mean, most things don't repeat forever, right? This is where Fourier's idea had to evolve into something even more powerful.
Yeah, what's the recipe for a one-time event, like a single clap of thunder? Or what about a static image, a photograph? These things don't repeat. So does Fourier's idea just break here? Not at all. The solution is just so clever. Imagine you have a repeating signal, right? But now we start stretching the time between each repetition. We just keep stretching it until the next repetition is infinitely far away. So what are you left with? A single isolated event. And that little conceptual leap, that's what gives us the Fourier Transform. It's the tool that takes the Fourier series and makes it work for any signal, whether it's repeating or not. It's basically a universal recipe book for the world around us.
Okay, so now that we have this universal tool, you're going to start to see its fingerprints absolutely everywhere. And I mean it. This isn't just theory, it is the foundation of our modern world. This is where the math really hits the road. It's the engine behind your MP3s and JPEGs. It's how Wi-Fi and cell signals fly through the air. It's what allows MRI scanners to see inside the human body. It's even at the very heart of quantum mechanics itself. It's everywhere.
In electronics, for example, simple circuits can act as frequency filters. They use these exact principles to let certain frequencies pass through while blocking others. This is literally how a radio tunes into your favorite station while filtering out all the other noise.
And get this, in optics, the crazy pattern of light you see after it passes through a narrow slit, it's described perfectly by the Fourier transform of the slit shape. So the exact same math that describes sound also governs the behavior of light. And this reveals this deep, fundamental trade-off that's baked into nature. See how a signal that's really sharp and precise in time, like this pulse here, has a Fourier transform that's super wide and spread out in frequency? You can't have perfect precision in both at the same time. And this exact mathematical relationship is the basis for the Heisenberg Uncertainty Principle in quantum physics. Yeah, that one.
Okay, so let's circle all the way back to that symphony in your pocket. How does Fourier's idea actually lead to compression? Well, it all comes down to the power of a good enough approximation.
So here's the trick. Compression works by taking that full, perfect frequency recipe and, well, it just throws out the ingredients that your ear is least likely to notice anyway, the waves with the smallest amplitudes. It creates a good enough version of the original sound.
And this slide just nails that trade-off, doesn't it? Fewer waves means a smaller file size, but you get a rougher, less accurate sound. More waves get you that beautiful high fidelity, but the file size gets much, much bigger. It's a constant balancing act between size and quality.
But, of course, this approximation comes at a cost. Near any really sharp change, like the hard edge of an object in a picture, you get this weird overshoot called the Gibbs phenomenon. Even if you use hundreds of waves, this little ripple effect never completely goes away. This is the very reason you see those fuzzy, ringing artifacts around edges in a heavily compressed JPEG.
So at the end of the day, our entire digital world is built on this one clever approximation. It isn't a perfect copy of reality, but a symphony composed from a limited number of simple waves. It kind of makes you wonder, doesn't it? What else in our universe is just a beautiful, elegant approximation?